I hope you are enjoying this picture drawing session. We have shown you some beautiful pictures of 1s and 2s orbitals already. Now in this module, which is going to be a little short, we are going to show you 3s as well, but before that let us complete our discussion of 2s orbital. We have shown you what 2s orbital looks like already. You get a node at r equal to 2a by z, and we have shown you how if we plot it in 3 dimensions we can get a depiction like this. Please do not forget that this vertical axis is wave function, nothing else, wave function. So from there you can generate this contour diagram, and what you see in white here is really the radial node where r is equal to 2a divided by z. And we also gave you this kind of a view. If you look from the bottom, you see these contours and you can see this big peak that is there inside. But that is only the orbital. What I do not have on these slides, but I have shown you in the previous module is that what happens when you consider psi square, and what happens, well, capital R square in this case, one and the same, and what happens when you multiply that capital R square by small r square and get the radial probability density. Okay. Now let us go back to this definition that we like to debunk so much, that an orbital is a region of space where probability of finding the electron is maximum. Well, the definition is there in so many places, there must be something in it, right. So let me just modify it a little bit and say that an orbital can be used to determine the space, the region of space where probability of finding the electron is maximum. Let me say that once again. An orbital can be used to define the region of space where probability of finding the electron with that wave function is maximum. How do you do that? Well, you have these curves, right. Well, you have psi star d tau. If you integrate, then what happens? Let me take you back to that plot. Maybe we will work in 1 dimension, well, 2 dimensions. Say this one, right. This is the plot of r square, capital R square for 2s against r. Okay. We are talking about radial probability distribution function. Suppose I want to know what is the total probability. What is the total probability? Well, I can say it without doing anything, total probability is 1. But if I am to get total probability is equal to 1, then I have to integrate from 0 to infinity, right. That is not something that we want to do. But one thing that comes out very nicely is if you just look at the numbers now, remember x axis is in terms of a0, okay. For z equal to 1, let us put z equal to 1 for now. This is 2a0, actually it is 2a0 by z. So if you go up to infinity, then probability of finding the electron is 1. Suppose I do not go up to infinity, maybe I will increase this a little bit. Right now it is up to 16, so let me make it up to 25 or something. Yeah. So while it is true that this function goes on until infinity, I hope that you will agree with me that it does not matter if I assume that if I work with the function up to a limit of say 15 angstrom, because beyond 15 angstrom is very little. So if I take area of this curve, maybe 99.999% of it will be there until this 15 angstrom or so. Beyond that you will have a very small amount of probability. So even though the orbital goes up to infinity, there is no need for us to go up to infinity. It is enough if we go up to 15. Now let us think like this. Let us say I take this radius of 15 angstrom. This is going to be 15 angstrom for hydrogen, right. Well, assuming Bohr radius to be 1 angstrom. It is not exactly 1 angstrom, so that factor will be there. So, let us say I go up to 15 angstrom somewhere here. So, probability of finding the electron inside a sphere of that radius will be how much? So, 99.999%. If I draw that sphere, then this surface of that sphere encompasses 99.999% probability of finding the electron. That surface is called a constant probability surface. So, if I want to draw a 99.999% surface, then perhaps I have to take a radius of 15. Suppose I am okay with say 95%. Where will I have to truncate? 95% will be somewhere here actually, yeah, maybe here. So, let us say 11 angstrom. If I draw a circle of 11 angstrom, then that circle would contain 95% probability of occurrence of the electron, right. So, this way we can draw surfaces, okay. And when we draw the surface, we might as well draw another circle inside it, because this circle of say radius 2 angstrom, well 2a0 angstrom is going to be the nodal surface. The nodal surface here, radial node, is going to be a sphere, right, surface of a sphere. So, we might as well draw that, because there is no probability density of finding the electron at that particular surface. So, that is how we often designate probabilities, and more often than not we mistake those plots to be orbitals. They are not. Those are plots of probability of finding electrons in particular orbitals. They are constructed using the orbitals. Okay. So, let us, I hope that we will not have any further confusion in this matter anymore. We have talked about constant probability surfaces, and let me show you some ways in which these probabilities can be determined. So, let us not think for a moment that probabilities are not important. Probabilities are all important. When we want to talk about things like bonding, we want to know what is the region where probability of finding the electron is more, what is the region where it is less, right. So, we have to work it out. So, how do you designate it? Well, this is how one can designate it. So, use different colors, okay. You put dots, more dots where probability is maximum. So, as you see, if you go out along a radius, density of dots here is more. As you go further out, density of dots decreases, and finally there is hardly anything, right. So, it is sort of like a galaxy, lot of stars, and then towards the fringe of a galaxy it fades out and then there is nothing, okay, something like that. It does not mean that it is actually 0, it is just that the density of dots is so few that you do not see it, okay. And inside you use dots of different color to designate the sign is different, sign of the wave function. Probability or probability density is always positive. So, sign of the wave function can also be conveniently shown in figures like this using colored dots. Well, another way in which you can show it is this kind of 3-dimensional Pacman kind of figures, where you show a section, draw a solid figure with one particular color, inside whenever the sign changes draw another solid figure. I like this one is prettier, but the previous one actually contains more information, because it sort of tells you at what kind of radius you have the maximum probability of occurrence. Okay. This is a more qualitative, definitely better looking depiction, but please do not forget these are not orbitals. These are using orbitals depictions of regions of space where probability of it is a depiction of probability distribution of these 2s electrons. Okay. These are not orbitals, orbitals have been used here. And once again let me thank Professor Shashidhar for having created these beautiful images almost 20 years ago. Okay. Now let us go to 3s orbital. 3s orbital, as we know, has a polynomial of second order. So, 3s orbital, remember, has in its expression a polynomial of second order, the 3 terms. So, polynomial of second order equated to 0 gives you 2 roots, and you can work out what these roots are. I think they are 1.9 and 9 if you just take z to be 1 and a to be 1. So, they occur in 2 different places. In fact, you see what the values are here. Okay. So, you have 2 radial nodes. So, when you start at r equal to 0 at the nucleus, you can start with a positive value of the wave function, it falls off to 0, that is a node, changes sign, then it has to rise again. So, there is a minimum point, then there is another node, rises again and falls off to 0 at well again asymptotically. Okay. This is 3s orbital. Once again we see that the innermost part is most, if I can say, intense, followed by the second part, the third part seems to have the least height. Okay. Once again when you multiply by r square, well, take square of this, multiply by r square, even though it is repetitive I will just do it for you. What was the expression? 27 minus 2x 18 plus 2x, I think. Please do not try to remember these expressions, as you can see I do not remember them myself, there is no need. Yeah, 27 minus 18x plus 2x square, that kind of an expression. So, I can write 27 minus 18 star 18 into x plus 2 x square. Okay, we have to get rid of everything else. And while doing all this, let us not forget that this factor is multiplied by an exponential term, and I will take you back in case you have not noticed what the exponential term is. The exponential term is e to the power minus zr by 3a. For our purpose we will set z to 1, a to 1, it will be z divided by 3. Let us see. So, we have seen the functional form for the 3s orbital. So, let me just put that in 27 minus 18 into x. Remember x here is actually r, what we have studied there, and I am not using z, I have set z to be 1. I am writing this in terms of a0. So, a0 is also set to be 1. So, all that is fine. So, simply I get 27 minus 18x plus 2x square multiplied by e to the power minus x by 3. Remember the exponential term, earlier it was e to the power minus x by 2, this time it is x by 3, and here it is. This is your 3s orbital. We have seen some depiction already, but here you have seen how it shows up when I key in the expression. This is what I get. So, not very difficult to understand. You have an exponential decay, that is why at x equal to 0 we have a maximum, and then you have a decay, but then this decay is modulated by this factor by which it is multiplied, which is a polynomial, and since the polynomial is of second order, it becomes equal to 0 for 2 values of x. So, here it is 0, here it is 0, and next it becomes 0 asymptotically at r equal to infinity. Okay. So, this here is your 2D depiction of 3s orbital. We will show you the 3D depiction also. Before that, let me do something. Let me take this whole thing, multiply it by itself and multiply it by r square. Here x is r. What am I doing here? I am trying to plot the radial probability distribution function, am I not? So, capital R square multiplied by small r square, that is what we are doing. So, this is what we get E. So, we have, of course, you have to zoom out even more, and then we will fix it. Okay, we have this is more like it, well, of course, you do not see anything here, but we will just take care of that in a moment. We started from minus 0.2, went up to 30. So, that is what we will keep now. Y axis we will have to see. Here actually we do not need anything in minus, maybe I will keep -1 or something, and we have gone up to 500 here. So, let us make that 510. Here you are. See what happened. Remember what the original wave function was? It had 3 portions, that is right, but at the center nearest to the nucleus it had the maximum value of psi, and then it decayed, went to 0, crossed 0, so that was a node, then turned again, crossed once again, and then went to another maximum, did that once again, finally went to 0. So, in these 3 parts that you had, this part was the maximum, most intense you can say, followed by this, followed by this. I am going to show the wave function once again, but the moment I multiplied by r square, after squaring the wave function itself, this outer lobe has become the major lobe. So, if you just look at the wave function, this looks like the smallest part, but the moment you take care of the volume element, which is simply small r square in this case, it blows up. Okay. So, let me just show you once again. I will take all this out. Now it is very simple, just have to change frame limits once or twice maybe and go back to the original figure. Let me make that look a little better. Yeah, see what I was saying, the outer lobe is actually quite small if you just look at the wave function, but well, let us see what happens when we take square of that. So, even the square of it, this part has blown up, followed by this, and this is what it is. Even if we take psi star, psi square in this case or capital R square in this case, what is it? Probability density. So, probability density is maximum near the nucleus, and then it has like smaller regions as you go further out. But the moment you multiply it by the volume element, component of volume element, small r square in this case, this outer lobe which had least probability density, at least in the maximal position, that becomes the biggest one. I wish I had better memory so that I would remember what the value was earlier. It will be the same value after all. Yeah, see. Now this actually has greater probability. So this is something that demonstrates very nicely the difference between probability density and probability. Even though probability density is minimum in this region, because of the volume element, probability is actually maximum. Okay. This is the point that I perhaps have said earlier, or perhaps I will say once again, but it is a very important point. It is important to understand. It is not just probability density, probability is also governed by the volume element that you are considering. Okay. So, this was in 2 dimensions. Let us now go over and show you the 3-dimensional plot. I will show you the 3-dimensional picture. Okay. This is your 3x for you, and draw the frame limits. We will draw it from 30 to 30, same here. This would be something like minus 3 to 30 or so. Okay, this is 3s orbital. First look, it might look exactly the same as 2s orbital, but actually it is not. You see, we have this sharp part for small values of r, then it goes through this first node and becomes negative, and then goes to the second node and becomes positive. Do you see this? This is the second node becomes positive. So, this is your contour diagram. This is the function. So, let us see that this orientation, if you can see in 3 dimensions, you can see this sharp and tall innermost portion, followed by the negative basin, followed by the positive small peak. So, let us see what happens when I take square of this and multiply it by your the volume element r square. Square of this multiplied by r square would simply be x square plus y square. Oops, it is blown up. Yeah. This is what it looks like. So, once again you can see the outermost lobe is the major lobe, followed by a smaller one, and you can hardly see the innermost one. Why is it that the trend has completely reversed? Because we multiplied by r square. For some reason the 2D plot seems to be a problem, but I think we have in any case shown you the result. So, we will come back to this one later. Okay. So, this is the plot that somehow we could not plot in real time, unfortunately something is wrong, but you are familiar with this anyway and you have seen what it looks like in 3 dimensions, and from there one can construct this 3 dimensional probability plot of 3s orbital. Remember, the color denotes the sign of the wave function and the density of dots denotes the value of not the wave function psi, not its square psi square, but psi square multiplied by r square. Okay. So, this is how we often designate the orbitals, but please remember these are not orbitals, these are using orbitals we have worked out the regions the radial distribution of probability of 3s electrons. So, as usual you can draw it like this, like Professor Shashidhar had done. So, we have talked about 1s, 2s, 3s wave functions. We have learned how to draw them in 2 dimensions and 3 dimensions, remembering that one of the dimensions is always orbital. We have also been able to plot for ourselves capital R square multiplied by r square, the radial probability distribution function. But one thing that is common in all these orbitals is that all of these are dependent only on r, there is no angular part. The plot thickens, the situation becomes more interesting when we go to p orbitals, where it is not only about r, but it is also about theta and phi. In the next module we are going to discuss p orbitals and d orbitals, and there we are going to learn where these px, py, pz and more interestingly dx square minus y square, dz square and so on and so forth, where these orbitals get their subscripts from.